record on this computer, share some screens. Cool. All right, so this week we're starting the real stuff. Not the real stuff, that's not true. But stuff, I don't know. It's hard to say whether it's going to be tougher. Let me get the polls going here and then I'll talk about it a bit more. There we go. All right, so the whole purpose of the last numeracy assignment sort of get you ready for this section the next at least 2 weeks, probably 3, well, maybe 2.5, whatever. And we're going to have to start doing multivariate calculus. Now, just for context, this is sort of a weird section. You know, up until now, we've really emphasized a lot about understanding and conceptual understanding. This section is here, though, just because econ is like, yo, you guys, you need to do this. And we're like, okay. But how can you expect us to do something that normally takes 12 weeks to do in 2 weeks? And they're like, you know, I don't know, figure it out. So the reality is we're going to blaze, yeah, stupid eco, exactly. So we're going to blaze through this portion. We are really going to emphasize procedure and sort of like computation. We're not going to worry too much about understanding. I mean, obviously we do want that a little bit as well, like understanding what is a multivariate function, what is a partial derivative, these sorts of things. How does Lagrange multipliers work? But this section is largely about just giving you the tools that you need to succeed in the event that you see these things at some point in your future, right? So I don't want to say that you should abandon comprehension. That's not our goal. What I do want you to do, though, is, you know, focus on the procedure here and, you know, getting comfortable with understanding what it is that we do. The reality is that even when we do teach this stuff in a 12-week course, MAT133, for example, is the course that would do a lot of this stuff. Even when we do teach it there, even there, it's very procedural. There is more of an emphasis on concept, but this material is actually so tricky and so difficult that it's hard to do even in a proper math course. And so even in those contexts, it's often fairly procedural. So, you know, obviously, certainly for us, because we're going to blaze through it, we're really just procedure. That being said, don't hesitate to, you know, ask tons of questions and try and get a good grasp on what's going on here. Interestingly, even though we won't make that tie explicit, there's a ton of linear algebra here, just a crazy amount of linear algebra. It's all linear algebra, in fact. No. So this question, the Hessian has to do with second derivatives, Connie, right? And we're not asking for any derivatives. I literally just want you to plug these numbers in and give me the answer. You know what I mean? I'm just saying, what is, you know, like if I'd said, if f of x is x squared, what is f of 7? And you'd say, oh, it's 49, right? Because you plugged that in. Nothing about derivatives. Here is a 3-variable function, right? So it depends on x and depends on y, depends on z. And I want you to plug these numbers in and just tell me what number I get, just to get us comfortable with, like, you know, actually playing around with these things. Oh, for sure. Yeah, Connie, there are definitely questions that are going to take a while, right? And yeah, kind of. I don't think I ever made you just plug numbers in. This is sort of like a nice little warm up to multivariate stuff, but assignment 11 was geared around getting us ready for this sort of stuff, right? That's why there were actually like 3 numeracy questions in A11, just to, you know, introduce us to the multivariate stuff. Because I don't think, probably nobody did multivariate functions in high school, right? Like they're no more complicated. It's still the same procedure. You plug numbers in, but you know, what's supposed to be review, I think for many of you probably isn't, right? Did anyone do multivariate functions? Not calculus, just multivariate functions in high school? No? Right, so I mean, this is to some extent us getting comfortable with that, right? And that's all it is. I just wanted to play with this, get a little bit comfortable with it, get a feel for how multivariate functions work. And of course, like, this isn't crazy. This isn't, you know, just us making you do math for the sake of doing math. The majority of functions in real life are multiple variables, right? Like everything. Think about like weather, right? If you want to predict the weather, what do you need? You need like temperature, you need humidity, you need pressure, you need, you know, a ton of things like that. You know, obviously it occurs a lot of math. We've seen even in linear algebra ways that you can have multiple variables, right? Here, you know, when we were doing linear algebra, everything was linear, hence the name. But you know, multivariate calculus is the study of nonlinear things of multiple variables. So that's why it gets harder out of necessity. Right. And yeah, this is not on the term test. This will be on your final though, but no, it's not on your term test. Okay, so I'm going to wrap this up in about 20 seconds here because this should be pretty quick. And most of the class has done pretty well here, so I'm pretty happy with that. But just finish this one up, and then we can get to some slightly tougher things, maybe more interesting things. Oh, Tara, so this is an interesting question. So let me take this up, and then I'll kind of address this. But the reality is that it's just not a super well-defined question, but effectively they're equal. Okay. So let's do this first. All right, and majority of the class said C. C is absolutely the correct answer. If you didn't get C, we want to make sure that, like, hopefully it was just a silly mistake, but let's see why it's the case. Because if we're having trouble just evaluating multivariate functions, then differentiating multivariable functions is really going to give us a hell of a time, right? So f of x, y, z. What was it? It was z squared over 1 minus y. Oh, maybe some people just maybe screwed up what ln was, right? Plus ln x. And we were asked plug in E23. Okay, so this thing here, E is the x, 2 is the y, z is the 3. And then we're just going to do it just like we would do a normal function, right? So z squared, that's going to give me 3 squared divided by 1 minus 2 plus 2 ln E, like that. And then we just simplify, figure it all out. 9 divided by -1 plus 2, so that's -7, right? And that is C. And don't forget, I think maybe what could have happened here, some students could have said ln E is equal to 0, right? Remember, ln 1 is 0, not ln E. But if you did, accidentally make that mistake, you would have gotten -9, which was D, and a couple students did say that. If that's what happened, I mean, for the most part, okay, tighten up your logarithms, but you still knew what you were doing, right? You just made a silly mistake. So that's, all things considered, that's not the end of the world. All right, everyone cool with that? Okay, I'm going to assume yes. All right, now same function. Why can't I scroll? Same function. Now I want you to find the x partial derivative. Okay, let me restart the polls here. So I want you to differentiate this with respect to x. Okay, remember when you do this, you're treating y and z as constants, right? That's what you do. Now, Terrace, you can't say infinity plus 1. That's not really a meaningful thing. Infinity isn't a number. So we don't just, when we talk about addition, we talk about the addition of numbers. Infinity isn't a number, so we can't really do that. What we can do, though, is talk about something to do with cardinality. And cardinality is how you prescribe how big a set is, including the different types of infinity. Now, if you have something, if you have a set which is infinite, and you throw another element into that set, you won't change the cardinality. You get the same infinity, right? Adding a single element won't bump you to the next level infinity. There are many different kinds of infinity, but yeah, adding a single element doesn't change the cardinality of your set. So you get the same thing. Mm-hmm. Yeah, tons of fun. Connie, is that... right, yeah, Connie, that's the right idea. Oh, you guys just did cardinality this week. Brandon, this seems a little late for you guys to be doing cardinality, but oh, last week. Okay, yeah, it seems a little late, but okay, sure. I seem to remember cardinality being much earlier. Yeah, and so everyone, there's sort of like, once you've solved this problem, there's this interesting thing about infinities. So there are many different kinds of infinity, right? And there are, in fact, infinitely many infinities. And there is no biggest infinity, right? If you ever give me an infinity, there's an infinity bigger than it. But if you put all the infinities in a box, the infinity which counts all the infinities is bigger than any of the infinities that it counts, and is not one of the ones that it counts itself.
I was gonna say, I'm pretty sure nobody caught that, Tyler. I think one here is they just kind of are gobsmacked for more than anything else.
And that's okay. So Brandon, there are infinitely many infinities. There is no biggest infinity. But if you count the number of infinities, that is itself an infinity. It is bigger than any infinity that it counts. And it is not one of the infinities that it counts itself. Okay, that's interesting if that makes sense. So Connie, do you mean like for this stuff? Because if so, take it slower. Terrace, this is like, yes, this is something that is fairly well known. You have to kind of dip into point set topology a little bit deeper, but basically the set of infinities is not a set. It's actually a proper class. And so in that sense, it's just too big to actually be a set. And there are people who just study this full time. Okay, so yeah, Connie, I think there's a lot there. In that case, what I want you to do is just step it back right now. Let's not worry about that stuff. Let's sort of like push Claroux and the Hessian and stuff. Let's sort of leave that for Thursday. And let's just focus one at a time, because it's true. If you're trying to take in too much, like it's easy to get overwhelmed, right? So let's just make sure that we're comfortable with partial derivatives first. So you did this question fine, right? What I want you to do is an exercise. Actually, I wonder if I'm going to do that later. So as an exercise, compute the y and z partials. And so for anyone who's done as well, this is something you can do as well. Compute the y partial and the z partial as well, just for practice, right? Just to make sure that you can actually do these things. Just give yourself a little bit of extra work there. Z is pretty easy. The y partial is a little bit of work, but not too much. And then let's just take it one concept at a time and try and build it up. Okay, so I'm going to close this down in about 30 seconds. See if you can get. This is a pretty straightforward one. Again, so we just want to make sure that we're comfortable with this. Because again, stuff only kind of gets harder from here. Okay, so I'm going to lock this up right about. Yeah, it is. Numeric, good catch. And I don't think the Y1 is in here, but good catch. The Z partial is actually an option. So it is actually one of these things. Okay, so we're going to compute the partial derivatives now. So we've got Q2. So a same function, right? F of X, Y, Z is, so Z squared 1 minus Y plus Y ln X, like so. Okay, and we want to compute the X partial derivative, right? So we've got a bunch of notation for that, di F, di X. This is a pain in the butt to write down a lot, right? So we often will just write this as di X F. And this is not a 2, this is not an alpha, it's like a curly D, right? Like check the PDF notes or the online book to see what this thing looks like. It's a curly sort of D thing, right? And so the partial of X with respect to F, when you do this, you treat all the other variables as constant. So in our case, we're going to treat Y as constant. We're going to treat Z as if it's a constant. And we're only going to differentiate with respect to X. Okay, so I'm going to write this out in like painstaking detail because it's sort of our first time doing it. But then after that, we kind of won't do it nearly as much. So when I look at this thing, okay, again, I'm differentiating with respect to X. Now this thing, there's no X's here, right? So this thing is actually constant with respect to, that's what WRT means, with respect to. This thing is actually constant with respect to X, and we know the derivative of a constant is 0, okay? So that thing's not going to contribute. Over here, the Y is constant, and the ln X is not, right? So we are going to get something. We're not going to get 0, but the Y really isn't contributing to the derivative here. It's just sort of along for the ride. Just like if I asked you to differentiate 2 ln X, it would be 2 over X, right? If I asked you to differentiate 7 ln X, you would get 7 over X. So the Y here is just a constant. It's just coming along for a ride. So when I differentiate Y ln X, I'm going to get Y times ln X like that. And that's Y over X. So that was option A right there. Okay, someone very cleverly pointed out option C is actually the Z partial. So dizf is 2Z over 1 minus Y. And then let's see if I can do the Y partial really, really quickly. So this is going to be negative, but I pick up an extra minus sign. So this is going to be Z squared all over 1 minus Y squared plus ln X. Okay. So again, those two, last two weren't really required, right? They were just sort of a bonus things, but this is so you can check your work if you did do those bonus ones. And a lot of the time, sure, can you explain, sort of if you'd be more specific, like what part specifically? And so again, right, a lot of the time you are gonna have to compute the X and the Y and the Z derivatives as well. Okay, yeah, is Z and Y. Okay, so when we take the Z derivative, same sort of story, right? So we take the partial with respect to Z, Z squared over 1 minus Y plus Y ln X. Okay, this thing has no Z's, right? So its derivative is just 0. And so we're gonna get, the derivative with respect to Z, Z squared 1 minus Y. Now the 1 minus Y is a constant, right? It also doesn't have any Z's in it. So we know you can take constants out of the derivative. And this is why when you differentiate, you then just get 2Z over 1 minus Y like that. Okay. And then for the Y derivative, again, you can sort of take the Z squared out. And you get die Y, 1 over 1 minus Y, plus, and then you can take the ln X out, die by die Y, like that, right? And that's how you get all the rest of it. Why is it 1 minus Y squared for the Y partial? So this thing is 1 minus Y to the power of -1, right? So that gives me negative 1 minus Y to the power of -2 times the derivative of the inside, which is -1. And that gives you that. No problem, no problem. Okay, cool. All right, everyone. So it takes a little bit of getting used to, because again, you see X's, and especially since, we're so used to differentiating X's, it's hard to think of it as a constant, but it takes a little bit of practice. But once you do it, you'll see this actually isn't that bad. Again, it is the sort of thing that I think when the first time, a couple of times you do it, it just takes a little bit to get your brain used to it, right? You've kind of been in this differentiate with respect to X mode, but do a couple of these until you feel comfortable with them. Now, this one's not too bad because for the most part, we were able to separate the X's and the Y's. We're going to do another one in a second here, not as straightforward because we sort of like mix the X's and the Y's together, and that's going to make our life a little bit trickier. Is this the one I want to do? No, let's go straight. Yeah, let's maybe do this one. This one's a little bit tougher. Okay, so this is only a function of 2 variables, not of 3. And I want you to tell me what the gradient is.
It doesn't really help, but the second function is the same for all of them. So realistically, all you have to work on is the first function, or the first part.
What?
Now I'm saying the second part of the function here is the same for all of them. So it's really only the first part that you're checking.
It's the same for all of them.
The x squared e to the xy is the same for all the options A, B, C, and D.
Oh, right. Oh, yeah, I see what you're saying. Nice.
Like
that's true. That's true.
You're only checking one partial derivative, not both.
Yeah. I mean, you should do the other one just to have it anyway. Yeah. But you're right. In terms of the partial, or in terms of the multiple choice, yeah, they're all the same. All right, so I have a question. You're saying like I give a bunch of options for what that upside down triangle is called, but what do I personally call it? It's sort of context dependent. I usually just call it the gradient. So I'll say gradient G. If I have to refer to it by itself, I'll call it nabla. I rarely call it del, almost never. So if I have to like call it by name, it's usually nabla for me. But in the context of actually applying it to a function, I usually just say gradient. All right, so I'd say here the gradient of G. Connie, right, yeah. Or I could just say, you know, even mathematically, you might just call this the derivative, right? The derivative in some sense. Okay, sweet. No, that's awesome, Connie. Yeah, I like to hear that, right? Like you're getting the hang of it. And that's awesome. Terrace, yep, exactly. And, you know, again, if we were doing sort of like a more rigorous course, the gradient has a, you know, sort of a separate interpretation. But for our purposes, absolutely, the gradient is just, you know, basically it is the vector of partial derivatives. So it says compute them all, right? Again, it has actually a physical meaning and interpretation that's actually really, really important. If, for example, it describes for you the direction of steepest ascent. But yeah, that's basically the idea. Agam, no, but once I do it, maybe you can, hopefully it'll clear it up for you and you can tell me what they're like, if you can show me what you did there, which is obviously a little bit hard to do in the chat, but I feel like you might have, it looks like you've sort of conflated the two and you know, because all the terms are there, they're just sort of in the wrong order. So we'll go through that though, and we'll see it. C1, sure. So you're probably a little bit ahead, right? Or you're thinking about us looking at C1. So Lee, what C1 means is that all the partial derivatives exist and are continuous, right? Now, continuous here is a little bit harder to define. Like it's not, you know, it's not too hard to think about what continuity means in terms of a single variable function, but in terms of a multivariable function, you should visualize it as being the same sort of thing, okay? So a multivariable function you can draw, and if it doesn't have any holes or gaps or jumps or, you know, vertical asymptotes, anything like that, then it's, you know, that function is continuous. So all C1 means is that all of its partial derivatives exist and they are all continuous. So Gurpratap, can you expand on that a little bit more? Like, what do you mean by what it would be? Like, are you asking for how to compute them? Are you asking for their intuition? Are you asking for, like, yeah, can you just be more specific there about what you need? Right, yeah, exactly. I would say everything that we do in this class, everything's going to be C1, so I wouldn't worry about it. It is possible to give examples of non-C1 maps, and there are, in fact, many of them, but for us, we're not going to worry about them, which means things like the absolute value because that was something that we ran into trouble with when we were doing single variable calculus. We had these like non-differentiable functions, or functions that actually we didn't see any of these, but functions that are differentiable, but their derivative is not continuous. We're not going to face any of these in the multivariate sense. They're kind of too tricky for us to play with the tools that we're going to have in hand. So don't worry about it too much, but a couple of the theorem statements require that we say the word C1. And so I didn't want, it was important that people weren't like, well, what the hell does C1 mean, right? So it was defined at some point, but just, don't worry too much about it. Okay, sure. We can talk about a bit more about that in a second, Gerbertab, because, I'm going to go into this in a little bit more detail. Everyone, I'm going to lock down the polls here in like 10 seconds. So just get your last minute answers in. Not 4 over x or phi, probably mean y over x. But what's the derivative of ln x? It's 1 over x, right? So y times 1 over x is y over x. And we're going to do a bunch more examples here. So for those of you who are still maybe struggling a little bit with partial derivatives, hopefully this will clarify a little bit. Okay, so 57% of the class said D. D is the correct answer. Very nice. All right, and again, if for those of you who are still struggling with like, how do I actually compute these things? Let's take a look at this. And then I'll show you guys, I'll pull up some graphing software and I'll give you some sort of idea about what partial derivatives are and what they really mean. All right, so here's a question. Actually, this is question 4. So we've got g of xy is x e to the xy, and we want to find the gradient, right? So we want to find the gradient g of xy. Now, in case you don't remember, the gradient is the vector of partial derivatives, right? So it's the x partial, oops, we're doing g here, and it's the y partial, right? Okay, so it just means, again, as was kind of pointed out by Terrace, find all the partial derivatives. All right, so let's start with the x partial. The x partial is definitely the harder of the two, but what we're going to do, so di xg xy is the derivative with respect to x, x e to the xy, okay? Now, for those of you who are sort of struggling with this, remember y is just a constant here, okay? It's not implicit differentiation, it's nothing like that, it's just a constant. So it's the same sort of thing as if I'd asked us to differentiate x e to the 4x, right? Like I think you all could probably differentiate this function. You know how to do that. Or if I changed it to a different constant, what if I did something like x e to the 10x, right? Or x e, that's pi, to the negative 5x, right? Like this isn't really going to affect the derivative. It is going to show up, right? But it's not really going to affect the derivative. And y is playing the exact same role in this partial derivative, okay? It's just a constant. It's just coming along for a ride. So when I differentiate this, I'm going to have to use the product rule, right? So I'm going to get the derivative with respect to x, derivative of the first times the second, plus x times the derivative of the second function like that, okay? And then I'm going to compute these derivatives. So the derivative of x with respect to x is just 1. And now the derivative, so when I look at this function, I'm saying, what is its derivative with respect to x? Remember, y is just a constant. And in that case, I'm going to get y e to the xy. Now, I know some students are going to be bugged about that. So let's kind of do this off to the side. So off to the side here, if I asked you what the derivative of e to the 4x is, that's 4e to the 4x, right? The 4, the constant, just comes down. It doesn't really affect the derivative. Same thing, if I had done the derivative of e to the 10x, I would have gotten 10e to the 10x, okay? So that constant, it shows up, but it doesn't really, do anything significant. It just kind of makes its way down. And then the same sort of sense, if I've got yx or xy, right? That y is just a constant here. So it's just like all the other constants going to come down like that. Okay, does everyone see that? You see how like in each of these cases that 4 comes down, that 10 comes down. And so again, I'm just pretending that y is a constant. So that y is just going to come down itself. Why is the x not removed when we differentiate it? Since it's only 4x, then it should be 4. Where? Not in the exponent though. Do you mean in the exponent? Right? Because it stays being 4x. Same thing with like the derivative of e to the x is real, like you pull down the 1, but you still get the e to the x, right? It's like a chain rule thing, right? So the derivative of e to the 4x is e to the 4x times the derivative of 4x, right? And then this here is why you just get the x out, but this thing up here should still be 4x. Yeah, okay, cool. And Devin, yeah, exactly. It is the chain rule, right? It's sort of like the chain rule. Yeah, I kind of answered it by accident, but you're right. Absolutely, it is the chain rule. Yeah. Okay. So for those of you who are kind of like bugged about partial derivatives, did that sort of help? Did that make sense? I hope these examples in particular really kind of show you like how we're treating those things as a constant. Yeah, no. So yeah, really, when I do things like say, so this goes back to the previous question, but I was sort of asked, to talk about, y ln x, right? So this is y over x, and the same reason, right? It's the same thing. If I had differentiated 4 ln x, let's say 7 ln x, because that looks like a y, what would you get? You would get 7 over x, right? If I change this to a 10, then this would be a 10, right? And if I change that to an 8, it would have been an 8, right? That thing is just a constant. So it's just coming along for the ride. That's what, I mean by that. So it's not really significantly affecting anything. So Rafi, does that answer you as well? Do you sort of like see, so that's not a 4, right? That's a y. So Rafi, does that make sense? Do you like see, because you were sort of specifically asking about that it's just a constant. So that's kind of, you're right, just treat it like a constant. And in fact, if you get into one of these situations, you're like, oh, damn, how does this work again? Anything you're not differentiating with, just replace by an actual number and then just practice it so you get a feel for what it is. You can't obviously write that as the answer, right? Like you can't replace the y with a 7 and then do it that way. That's not how it's going to work. But if you ever get into one of those situations where you're just like, oh man, I'm really having trouble visualizing what's supposed to happen here, just do it on a little scrap of paper on the side and be like, oh yeah, okay, that's how it should work. And then replace your constant with a y and sort of do it like that, okay? And that should be a technique which allows you to, get comfortable with doing this sort of stuff. Sure, maybe just remind me towards the end, Ahmed. Okay, so that's actually the x derivative, right? So, and if we check, as Aziz kind of points out, all of the second coordinates were all the same. So really, once you have the x partial, you know what the gradient is. The only one that matches this is d, right? So d is e to the xy plus xy e to the xy. So that one's d. We should do the y partial while we're here though, right? Just for the practice. So if we take the y partial, so it's going to be the derivative with respect to y, x e to the xy like this. Okay, remember the x's are constants, right? So again, if you're comfortable going straight to the answer, phenomenal. But what it might help you to do is say, okay, well, the x is a constant. So let me just sort of take it out, right? And then same sort of thing as before. Now I'm differentiating with respect to y. X is just a constant. So it's coming along for a ride. And we're going to get x, with respect to y. So we're getting x e to the xy like that. And that gives me x squared e to the xy. Okay, so that's our y partial. Now, what I would strongly recommend, so I think some of you probably even still use Desmos for this, and I use Desmos for a lot of my 2D plotting as well, but for 3D plotting, some things are better than others. And I would strongly recommend the following. Okay, so let me just share something here. Which one do I want? Yeah, so this one. So I would sort of more recommend this website personally. So this is math3d.org. And this is, I think, a little bit better in terms of doing your 3D plotting, right? So you can do things. So here, let me actually like put in the function we just had. What was it? X e to the power of xy, like that. And, oh, fine, have it your way. All right, so here's what it looks like. It's not a very interesting looking function. Ugh. Okay, never mind. Now it's more interesting. So apparently I can't be as sloppy with this as I can be with Desmos, right? Desmos would know X times Y. Here I actually had to put in my multiplication signs. But here you can see, you've got a rough idea of what this function looks like. And we can extend, maybe the domains. You always have to be a little bit careful with your 3D plots because it takes a lot more points in order to figure out what they look like. But this is what this function looks like, right? So, no, but actually this isn't crazy, right? So here's the thing. If I all right, so here is like if x is a constant. And the idea here is that this function actually looks like e to the x basically, right? Or 2e to the x. So if you sort of look at it in one of the coordinate planes, you get an idea of what this thing looks like, right? Exactly, now it's Desmos, right? Versus if I looked at it like this, again, my y-axis here sort of goes the wrong way because my y-axis goes from, right to left here, but same sort of thing, right? It looks sort of like e to the x, just sort of facing the wrong direction. And then when you combine those two things together, you get this. And this is really, I really like this software because it really, I think, helps you see what's going on, not 6. So, it helps you, for example, see that this thing is a bowl, right? So x squared plus y squared, this thing is a nice little bowl here, like so. Something really nice happens if you change that to a minus, you get this thing that is called a saddle, right? So mathematically we call this a saddle, and hopefully it's obvious why. It looks sort of like a saddle, right? You might put that on a horse or something. And so everyone, what actually happens here? So you can see we've got our x-axis here, right? We've got our y-axis here. Z is just the dependent variable. So what the partial derivatives do for you, remember, we know that the derivative is supposed to tell you the rate of change, right? The instantaneous rate of change. And we can't do that on a surface, right? I can't tell you how things are changing because it depends on which direction you're traveling. So what I want you to do is I want you to imagine you're sitting right here at the origin, right? Okay, you're sitting at 0, 0, right on the top of this saddle here. What the x partial derivative is, and hopefully look at this expression, the x partial derivative is 2x, right? So what that's telling you is that if you moved in the direction of x and x only, okay, you keep y constant. So if you move in the x direction, it tells you the instantaneous rate of change of the function in the x direction. Okay, so in this case, the rate of change is 2x. And that's not surprising because if I look at this thing, oops, maybe let me do it like this. If I look at this thing sort of head on, that looks like just sort of x squared there, doesn't it? Right, that looks like x squared. And so we expect its derivative in the x direction to just be 2x. Now, the y partial is going to be negative 2y. And again, sort of the idea is that if I look at this, you imagine if I look at this so that my y-axis is pointing to the right, I'm going to get something which looks like negative y squared. And there you go. Doesn't that look like negative y squared there? So when you kind of look at it on its side here, you get this idea that this function looks like a negative parabola, right? But if I look at it so that the x-axis is like this, now it looks like a positive parabola. And what the partial derivatives tell me is how quickly is this function changing in that direction, right? So if I'm moving in the positive x direction, how quickly is my function changing? All right. The gradient from a geometric viewpoint. Now, I'm never going to test you on this, but this is sort of like an important thing to keep in mind. What the gradient does is it points to the direction of steepest ascent. So you imagine you're on a mountain that looks like this. This is a weird mountain, right? But it's a mountain. And you're right here on the mountain, okay? And you want to figure out, okay, if you're trying to get to the top of the mountain, which direction should you travel? Should you travel this way? No, that's not going to get you up the mountain very quick, right? Should you travel this way? No, that's actually going to take you down the mountain, right? So if you're standing right here, the gradient actually tells you what direction to move in order to go up the mountain the fastest. Okay, so in that case, you can probably see it's going to be like this direction. Okay, so the gradient always points the direction of steepest descent. And this means that it's important for doing things like computing maxima and minima numerically. It's, it ends up being just super important because it's often really useful to know, how can I make this function as big as possible, or how can I make it as small as possible? It's going to show up a lot when we do optimization and that sort of stuff. Okay, so I really recommend math3d.org. I found in my experience, it's definitely sort of the best 3D browser-based plotting software. It's pretty solid. You can mess around and do even implicit surfaces like this. I do think it is better than Desmos for this, and would strongly recommend that you use this if you want to get a good intuition for what things look like. Okay, and there are discontinuous functions. Absolutely, there are, and when you plot them, will have like weird big jumps in 3 dimensions. And one of the hardest things I think about doing multivariate calculus is visualizing these things, is getting an idea for what they look like. So hopefully that bit of software, math3d.org, gives you a little bit of a hand there. All right. Now, let's see. So we got about 10 minutes left. Maybe let's do one more quick one. So I'm just going to give you a polynomial here, something pretty easy to differentiate, but that's not going to be the point, really. So let's do this one. See where we can get on this. Okay, and we want to find the points where the gradient is equal to 0. And spoilers, that's going to be called a critical point, right? Where the derivative is equal to 0. It's going to be important for finding maxima and minima and all the usual stuff. But what we're going to find is that finding critical points for functions of one variable wasn't too bad. For here, it's going to be much worse in general.
It's funny because we're pretty much going to redo the whole previous section, but with multiple variables. That's kind of the only difference. So it definitely gets a little bit harder.
But it makes everything so much worse.
Yeah, it does. But like, if you have some good intuition, I'm pretty sure you can guess what the next 3 topics we're going to cover are before you even talk about it, just by looking what we did after. We did critical points in first derivative with singular functions. So
yeah, absolutely. And again, that's the whole reason, right? Like econ wants us to do this stuff for like Lagrange multipliers and stuff, which is all about, increasing and decreasing. No, and it's too hard for you guys to figure out what discontinuities of a function look like, of a multivariate function. And multivariate functions are really tricky in that they often have discontinuities, and it's not at all clear that they have discontinuities, right? Like, I think you can look at a function of one variable and be like, oh, yes, I can see that this function is probably going to have a discontinuity here. With multivariate functions, it's much, much harder. In finance, I don't know. You'd have to ask Aziz that. I am not altogether certain where it comes, but this is mostly for the econ.
Econ, I was going to say, this like directly more correlates to econ, like for your utility curves and your elasticity functions a lot more than for finance. For finance, you won't necessarily use multivariable like gradients and derivatives, but you see it even a little bit if you take like what's it called, the options course in 4th year in finance. You see a little bit more in effect there, but not to this high level. I feel like it's a bit more on a sorry, it's more of a high level. It's not more of a detailed level, I guess. That's kind of generally speaking. Yeah, you maximize utility. You see it in utility function. You see it in elasticity calculations. So it has a couple of use cases, like very, very prevalent use cases in economics. Finance, the thing is with undergrad finance is it doesn't necessarily go in depth about some of things, how some things really work. But some of the like 4th year option classes, like put options, call option class, I think they're called just options classes usually. They kind of dive a little bit into derivatives, which is kind of cool, but nothing too like crazy. So yeah, it's not until you get to like a master levels of finance where you see this being full-fledged used a lot more in detail. So that's way down the line, I guess, but it's good to know where like the basis of this comes from.
All right, let's. It's going to depend on the work that you do, right? Certainly, like there are lots of people who will use this, but whether you would do it in finance, probably not.
I worked in finance after graduation and for like a year and a half, and I didn't use this. I'll tell you that much.
Yeah.
This is a bit too I guess complex. Not necessarily just complex. It's tough because it's hard to model functions like this level of accuracy in the real world. So it's usually a little bit of different methods that we use rather than just simple finding derivatives. So not necessarily as much. Maybe in grad school when you're doing more of the theoretical stuff, you'll see it more but not necessarily in the practical world, I guess, as much. If you're talking specifically about finance, at least.
Okay, now while you guys are working on that as well, here, let me share with you another function. So hopefully you've memorized this x to the 4 plus y to the 4 minus 4xy plus 1. So here, I'm going to show you a different function here. So here's a function, xy squared divided by x squared plus y to the 4. And this function, it's a little bit hard to tell, but it's so badly behaved near 0 that the graphing software just kind of doesn't even know what to do, right? Like you can kind of see here, it kind of starts to freak out, right? It gets upset.
That looks horrible.
Yeah, and it's not, again, it's not as clear that this function is actually badly behaved here, other than the fact that it's doing weird things, and you can see that it's doing weird things. But this function is not continuous at 0. And it does actually, I mean, it's certainly, it's not even defined at 0, but it doesn't even have a limit as you approach 0. Okay, so there are no limits as you approach 0. And so this function is really has an essential discontinuity at 0, but it's a little bit hard to see it in the graph, right? So this is the sort of thing, like, we're not going to ask you to do this, because how would you even be able to tell that this thing has an essential discontinuity? We'd have to introduce a lot more tools for you to be able to do that, right? So we're not going to worry about that stuff, but just so you get an idea that there are some, nasty functions out there. Now let me throw this back up. So okay, and I'm going to call this pretty quick here. It's good to see most of the class has this, but let me nail this down in like 10 seconds. So get your guesses in. All right, let's take a look at that.